So let's begin implementing insert the function based on the recursive design idea there. So here we need to insert the function available publicly so that from T1 object we can call insert. So in the public interface, we need to define insert the function which takes data there. So let's do some sketch of implementation. Insert integer data there. So in recursive design step, what we are going to do is if data on the root is greater than we are going to insert onto the left subtree. So here we are going to utilize induction hypothesis. Utilizing induction hypothesis means a recursive call. So when you call recursively for insert function, I need to specify which tree, either left subtree or right subtree. So it seems that insert function should need another parameter in addition to the data to be inserted, insert where. So the eventual ultimate form of insert should be bs3 and insert and then which binary search tree. So which binary search tree is always pointed by a pointer points to the top of the tree as like a root p. So we need a root pointer and then data. This is the ultimate form of insert function, so that when you call recursively, we can specify onto which tree we are going to insert. So this one should be utilized within a public insert function. So here is that as we insert data, insert onto the entire tree, this data, something like that. Then the root may be updated as a result of the insertion and the like. So this public function will utilize another insert function designed for recursively. So this is not for public use. So we could put that in private function void insert, and then which tree and what data should be the form for recursive design. Then why do we do assignment? Let me explain this. Since we are going to have a new tree assigned, so it should be return value should be a root pointer. So let me correct this one. As a result of the insert, a new tree may be returned. So let me explain why we do something like this. So the very first time as we insert, so let me clean the screen here. So when T1 object is created, T1 and then root P is pointing to null. That's what we have designed for BS3 constructor. And then we do first insert. Then we are going to, since it's the very first one, 5 is stored. This is node structure. And then the root P should point to the new node. So as a result of the insert will return an address which is the top of node. So root P would be updated as a result of insert. So that's why we have this return values. As a result of insert, the root P pointer to the root of the tree may be updated. Now we are ready to utilize the recursive function design. So recursive function design, if the problem size is trivial, a base case we could solve directly. So trivial size is if whatever tree provided has no data at all. So size is 0, then that's a base case. Then we could assign a node there, the very first thing, create a node, and then that becomes a root of the tree. Then eventually when done, we return the new root of the tree. So that will be updated. So that's the very first case, trivial case. And then let's continue implement that. Else, if then the data to be inserted is smaller than the data at the root of the current tree, then we are going to insert the data into data is smaller, so we are going to insert the data into the left subtree. So left subtree, the tree is represented by the address of the root node. So on the left subtree, the top node on the left subtree is left. So that's a left subtree, and data will be inserted there. And as a result, the left subtree root may be updated as I showed you here. So if you do the very first insertion, the root may be updated accordingly. So similarly, if data to be inserted is greater than data at the current root node, then insert onto the right subtree the data. As a result, the right subtree may be updated there. Then else case is the data is the same as the data at the root is the case. Then one of the binary search tree assume that unique data only, like said in math. So that is the thing we have assumed in binary search tree implementation. So we can ignore the rest case. So that's the implementation of insert the function. Now we have the data here. Let me erase the screen. And let me first compile and run. It works fine. Then let's test this. So breakpoint, debug, start debug. So it's Mac specific ones. Sometimes to use the debugger, we need to set some privilege there. You will not see this on Windows. So we have T1 at this moment. We have a T1, and the root P is pointing to null. Now let's verify that, and debugger console, and the T1 root P is null. PTR is a 0 value. Then let's step over, so insert the 5. So at this moment, what you get is a node is created, data 5 is stored there, and then no left and right, but root P is pointing to the very first node. So let's verify that. T1 root P is pointing to something. So what is there? Data 5, left is nothing, right is nothing. So let's do step over. Then what you got is 4 is inserted. So 4 is less than 5, so 4 will be placed here. Then 7, as we do step over, 7 is inserted, and 7 beginning with the root 5. 7 is greater, so it will be placed on the right of 5, like this. So let's verify the structure. Debugger console. T1 root P. Then is pointing to 5 left, so which is 4 is the data pointed by left, and then right 7 is there. So we have this structure, and as to the node with the 4, left is not null pointer, right is null pointer. As to node with 7, both are null pointers. So we verified the operation of insert. Let me verify just one more thing. Now if I do T1 insert 3, like that, then compile, then let's set the start the debug, and step over there. Then 3 should be on the left of 4, so let's verify that. T1 root P, so 5 is at the root, left 4, and the left of 4 is 3, so we can verify the structure.